Welcome guys. Welcome to the course of Operation Research. And today we would like to discuss the introductions to discrete Markov chains. So this is the basic understanding of stochastic process and also the discrete Markov chain. So the references, this is taken from the book of Introduction to Probability Models and also some online resources. And guys, to take a look at these conditions, so there's a shifting from snow to sunshine, and then sunshine to the rain, and this is the probability, right? And also when we toss a coin, there are two sides, right? Side A and side B, and then after we toss, and then we will see what happened, what will be coming out. And also this is the case of COVID-19 pandemic. If you look at this website, and then you see that the numbers of active cases and also the number of people suffering, and then that people survive, and the number of deaths. And yeah, so what is the common issue of those phenomena? Of course there is similarity in terms of change of state, so change of the conditions from A conditions to the B conditions, from B condition to the C conditions, right? It's like when we toss a coin, and then there will be side A, the numbers, and also side B, the picture. And also when it's snowing to the rain, and today it's rain, and tomorrow, and I don't know, that will be rain or not. But in terms of changing of season, yeah, that will be a shifting of seasons, but we haven't had an idea how long exactly the time, but we can predict, right? And also the number of patients that positively yeah, suffer from COVID-19, and the two things will happen, right? They will survive, or they will yeah, not survive. It means that there will be suffering a lot, or there will be death. Okay, so it is a probabilistic, it is a stochastic model. Okay, stochastic process. So a stochastic process is a process that evolve over time in probabilistic manner, and stochastic process is represented as an index collections of um, random variable. Okay, random variable, we call it xt, where the index t runs through a given set of t. Okay, often t is taken to be the set of non-negative integers, and xt represent a measurable characteristic of interest at time t. So we have x and we have t. T is time, x is a random variable. Yeah, the collection of random variables. So x can be, for example, yeah, random variable at times t when it is rain, and when it is not rain, and etc. Okay, the stochastic process in general having a structure. The status of system today is one of the m+1 category, which is mutually exclusive. We call it states. So state is a condition. This is the status from the system at time t. So the values will be 0, 1, 2, 3 until m. So this is just a code, right? A code. So system can be observed in several point of times, and uh, which has yeah, we can use symbols t equals to 0, t equals to 1, t equal to 2, and etc. So all the stochastic process xt that consists of x0, x1, x2, until xm, representing mathematically how the status from from uh, current conditions will change to the next condition. So this is called stochastic. Then more specifically today, we will focus on the Markov chains. So the Markov chain is a stochastic model that describes a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. So, the future depends on the previous condition. Okay, so now is depend on previous one. Future depends on now. In a simple thing we can say like that. So in continuous time, it is known as Markov process. It is named after the Russian mathematicians Andrew Markov. So if you look at here, they say that in this continuous time. So if we have a continuous time, we have a discrete time. Okay, so Markov chains have many applications as statistical model of real-world processes, such as, for example, studying cruise control system in motor vehicles, queuings or lines of customer arriving at the airport. Like the previous week, we studied about the queuing system, right? And also the currency exchange rates and animal population dynamics. Okay, so this is the guy called Markov, Andrew Markov, that proposing Markov chains. So what is Markov chains here? So please take a look at the this one at P when x plus 1 equals to I x n plus 1, and with the condition of xn equals to in. So it means that so if you look at here, there is a one difference, okay, one difference period of time, which is 1. So given, so this is a condition, right, conditional. So given x in n equals to in, that will influence x in n plus 1 equals to in plus 1. So the current depends on the previous, the future depends on now. Okay, and we have a transition probabilities. So chain of condition, we call it transition. So I will talk about it later in the subsequent slides. So this is just give you understanding that, so Pijn, it means that probability, transition probability, transition from I to j. Okay, a period n is a p xn plus 1 equal to j with the conditions xn equal to I. So given condition I and become j from period n to n plus 1, we can say that it is probability called Pijn. Okay. So types of Markov chains. Okay, we have discrete time, we have continuous time, as I mentioned previously, and we have countable state space and continuous or general state space. So usually for this course, I will focus on this one, discrete time and countable state space. This is discrete Markov chains, and discrete time Markov chains on a countable or finite state space. But if the time is continuous, so it is called continuous time Markov process or Markov Chain process. So usually for discrete time, it is called Markov chain. But continuous time, it is called Markov process. And this is a continuous or general state space. Yeah, we call it Markov chain on measurable state space. but this one is for continuous. Okay, they call it continuous stochastic process with the Markov property. This is very, very complex. Okay, so discrete and continuous time Markov chains. Usually the term Markov chain is reserved for a process with a discrete time, a discrete set of time. There is a discrete time Markov chains. And for continuous time Markov chain, it is called Markov process. So it is a different, to differentiate between discrete and continuous time regarding the Markov. Okay. Okay, transition and state. Yeah, this is just a review from the previous slide. So transition and state is very, very important in Markov chains. The changes of state of the system, it is called transitions. So transition is changes of state of the system. So change from certain conditions to another conditions. Yeah, it changes. This is called transitions, and it has a probability. So the probabilities associated with the various state changes are called transition probabilities. So the process is characterized by a state space, a transition metric, okay, transition metric describing the probability of particular transitions and initial state or initial distribution across the state space. Okay. So this is one example of for illustrations about the transition metric. So let's see that we are now in the time t. Okay, now it's time t, and the state we have S1, S2, S3, and S4. So let's see, this is yeah, we let's imagine this is maybe this is rain, dry, summer, and winter, for example. Just an example. And this is the time t plus 1. Okay, time t plus 1. 1 is depending on the context. Can be 1 year, can be 1 day, 1 minute, and can be 1 hour. Okay, depends on the context that you observe. So it also make the S1, S2, S3, and S4. So let's say that this is one example, 832. What is it? This is the probability that the state changes from S3 to S2. So this is the probability, we call it 832, or it is a probability given S3 and it become S2, or probability S2 given S3. We call it A32. So more about Markov chains. The simple two-state model from the previous lecture, okay, was defined by 4 transition probabilities. Okay, it is called a transition metric as well. So this is one example as well. So the state only 2, A and B. Yeah, A and B. So A to A means that the current state is A, and then the future state also A. So the probability is 1 minus B. So from the current A, and then it become B, and the probability become B. So yeah. So can you see here that 1 plus B plus B, 1 minus B plus B become 1. So in total, the probability given A, given the state A become A and B, the total will be 1. And also this one, Q plus 1 minus Q, it become 1 as well. So the total probability is 1 for any conditions, the future state given the current state, right? So this is also an example of transition metric for the current state, sleep, run, and ice cream, and then sleep, run, and ice cream for the next state. So it means that the people or person now is sleeping, and what is the probability in the next hour, for example, of running? So it becomes 0.6, and the probability from sleep and eating ice cream is 0.2, and sleep again becomes 0.2. So the total will be 0.2 plus 0.6 and plus 0.2, if the total will be 1.0. Okay, so I think I have 4 cases. Yeah, because this lecture is just an introduction. So as long as you know the concept of Markov chain. So case number 1, the weather in the city of Surabaya can change quickly from day to day. Even so, the chance to dry, not rain tomorrow is greater if today is also dry than if it is raining today. And the probability of dry tomorrow is 0.8 if today is dry, but only 0.6 if it is raining today. So this probability doesn't change if information about the weather before today is also considered. Okay, and I think the weather changes from day to day in Surabaya is stochastic model. Okay, stochastic process, I mean. And starting on a certain day, we call it day 0. The weather is observed every day. Okay, every day. So from t equals to 0, 1, 2, 3, and etc. Okay, the system state or status of t day is 0. We define to be dry. It's just a code, right? And 1 become rain. So for t equals to 0, 1, 2, the random variable xt contains the value xt equals to 0 if dry and xt equals to 1 if rain. Okay, so it is very important that from the descriptions of example case studies, you should define, okay, you should define what's the changes of state. So here the state is dry and rain. Okay, and case number 2, how we make a transition metric for case number 1. So the transition matrix for case number from the case number 1 is that, so we define a state here is 0 and 1, 0 and 1. So this one become, okay, 0 from 0 to 0 and p 0 0, and then 0 to 1 is become p01. So this is 0.8. Okay, if it is dry and tomorrow also dry, is 0.8. But if today is rain and tomorrow will be if today is dry and tomorrow will be raining, then it becomes 0.2. So it is makes sense, right? Because it's given in the previous example that it is knowledgeable that if today is dry and the probability that tomorrow will be dry as well is greater than become raining, right? Because yeah, based on the historical data, the condition for today is followed by the condition depend on the condition of yesterday with the same state. Okay, but it's not always true. It's not always like that. It depends on the on the data, on the situations, on the conditions. And you see that here b00 plus b01 equal to 1, and b10 plus b11 become 1. So this one 1, this one 1. Okay. Case number 3 is Pac-Man. So I think everybody knows, right? Pac-Man. Yeah. This is Pac-Man eating, and there are goose here, right? So Pac-Man, the image to the right describe a discrete time Markov chain with the state space 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there will be 9 state space, and this also 9. So 9, it means that state space, right? The up in the space from 1, 2, 3, 4, 5, 6, 7, 8, 9. And the player controls Pac-Man through a maze, eating Pac dots. So meanwhile, he is being hunted by ghosts. Okay, for companion, the maze shall be a small 3 times with grid, and the monster move randomly in horizontal and vertical direction. So a secret passageway between state 2 and 8 can be used in both direction. Okay, So draw the transition matrix. So just please take a look here. There is arrows from 1 to 2. It means that from 1 to 2, the probability is half 1 over 2, right? From 1 to 4, it's also 1 over 2. And also here, like from 8, it to 2, and it has 1 over 4. 8 to 7 is 1 over 4. And 8 to 9, it's 1 over 4. And also this one, it can be 8 to 5 is 1 over 4, and also 5 to 8 is 1 over 4 as well, because there is 2 directions. So from this from this chart, you can draw a transition matrix like this one. Okay, this is a transition matrix. So I think this is okay, right? But the blank here is it means 0. So I didn't put 0 on the blank space here. Okay, but make sure that the total probability for each state in horizontal here is 1. Okay, and the last one is gambling ring problem. It is the gambler's ring problem. At time 0, I have, for example, at time 0 for now, I have $2. At times 1, 2, and etc. I play a game in which I bet $1. Okay, with the probabilities P, I win the game. With the probability 1 minus P, I lost the game. So my goal is to increase my capital to 4 to become $4, and as soon as I do, the game is over. So the game is also over if my capital reaches to 0. Okay. Let's X represent what? My capital positions, right? My capital position is what? So my capital position is the number, the amount of money, right? The amount of money, it can be, minimum can be 0 if I don't have any money, right? I don't have money at all because I lost everything, even though I have $2. But when I do game, I lost, and my money becomes 0. So, and maximum I can get 4. Okay, I can get 4. So the state can be 0, 1, 2, 3, $4, and also this one 0, 1, 2, 3, $4. And then x0, x1, x2 may be viewed as discrete times stochastic process. So for example, from 0 to 0, yeah, of course. So I didn't play anything, right? So the probability become 1. And from 0 to 1, why 0? From $0 to 1, 2, 3, 4 become 0. Of course, because if you don't have money, it means that you have $0. So you cannot play the game, right? You cannot play the game. If you cannot play the game, of course you cannot add money at all. So all the probabilities become 0 here. But 0 to 0, of course, yes. You have 0 now, and in the future you also have 0. But take a look at here. If you have $1, and you play $1, right? You can win, right? You can win. Then if you win, then you become $2. But if you lost, then it becomes $0. So if you win from 1 to $2, you win the probability of P here, right? P. And but if you have 1 and then it becomes 0 and then you lost, right? It becomes 1 minus P. Okay, and the rest will be 0. Okay, let's make sure that the total will be 1. So 1 minus P plus 0 plus P plus 0 plus 0, it become 1. And also the rest, right? So yeah, I think that's the basic of Markov chains, guys. So this is, I think it's for today, for the introductions of Markov chains. This is enough to understand the concept of Markov chain, also the transition probability. And I will follow up with some example or assignment to make you understand more. Okay, thank you guys. See you.